Let's consider the function f of t equals t squared. I'm trying to find what's called a Fourier polynomial for t squared of a certain degree. Realize when I say the word polynomial in this context, it's not the same meaning of the word polynomial as you've always learned. It's a quote-unquote polynomial whose terms are trig functions for the most part instead of powers of t. Fourier polynomials are a stepping stone to understanding Fourier series, which are infinite sums, infinite Fourier polynomials, you might say. Series, just like in Calc 2, means infinite sum. And Fourier series, as you'll learn about if you watch the lectures thoroughly, are helpful for solving partial differential equations. So this is a function in some function space. What function space? Well, lots of function spaces. The convenient one to pick for the sake of talking about Fourier polynomials is C negative pi to pi. It's not the only one to pick. I could also pick C 0 to 2 pi, or any interval of length 2 pi is most convenient here, but the one we'll pick is negative pi to pi. What again does this stand for? This stands for a vector space. The elements of the vector space are functions, real valued functions that are all continuous on this closed interval from negative pi to pi. It's an infinite dimensional vector space. It doesn't have a finite basis. Okay, kind of blows your mind. But we can consider finite dimensional subspaces of this. W to say be the span of a finite collection of functions. And the collection of functions you want to pick for the sake of doing Fourier polynomials and Fourier series, well, you start with the constant function 1, then you pick cos t, cos 2t, cos 3t, etc. How far should I keep going? If I want a finite set, I better stop somewhere. Call the last one cos nt, and then sine t, sine 2t, sine 3t, etc. through sine nt. Okay? It turns out that all 2n plus 1 functions here, 2n plus 1 functions, wait a minute, I thought I got rid of my red pen. 2n plus 1 functions there, they're all mutually orthogonal. This is an orthogonal set. But wait a minute. What do you mean they're orthogonal? It means what do you mean? Their graphs are perpendicular or something? No, I don't mean their graphs are perpendicular. I mean they're orthogonal with respect to a certain inner product. The inner product is this. The inner product of f and g is the integral of f times g over the given interval. And by the way, I didn't mention this last time, but you know, integrals are supposed to be analogous to summations. When you do ordinary dot products, you are doing a summation of some products. Oh, that's what we're doing here, a summation, quote unquote, an integral of some products. This is completely analogous to ordinary dot products in this context, but we call it an inner product. They're orthogonal with respect to this inner product. I could make other inner products which they're not orthogonal with respect to. So which ones are right? It depends on the application. And for the application of Fourier polynomials and Fourier series over this interval, that's the inner product you want to use to make the most sense out of it. Okay? They can be orthogonal with respect to one inner product, but not another. How weird. So what does it mean that these are all mutually orthogonal? It means if you plug two distinct functions here into this inner product here and do the integral, you'll always get 0. For example, you know, if I did cosine of 3t, sine of 4t, I won't actually do the integral. I'd have to do this integral. And it does turn out that that equals 0. Is that difficult to show? It's not super easy. There's 2 approaches I think you could take to showing that. I think you could use integration by parts, though you have to use it twice and you'd have to do some algebra. letting like u equal cos 3t and dv being sine 4t dt. It would seem like you're going in circles. You'd have to use it a couple times and you'd have to do some algebra to solve for the unknown integral. That's one way to do it. A more direct way, if you have something where you can look this up, is you can use a table of trig identities. I'm not sure which Mathematica command might give you the right trig identity to help you see that this is zero. For example, these are all mutually orthogonal. It's an orthogonal set of quote unquote vectors, and therefore it's actually got to be a linearly independent set as well. And therefore it's got to be a basis for whatever subspace it spans. Yeah, W will be a 2n plus 1 dimensional subspace of this infinite dimensional space there. Can I visualize this? Well, by analogy, and maybe just to up the dimension, maybe I should imagine a 3-dimensional picture. Imagine this plane to be W. Now, W is not a plane, but use your imagination. Pretend that's a 2n plus 1 dimensional subspace of, well, I've drawn it to look like 3-dimensional space, but pretend 3-dimensional space is representing infinite dimensional space. F of t equals t is a point in that infinite dimensional space. In trying to find the Fourier polynomial for f, what I'm really doing is I'm finding the orthogonal projection of f onto w. Call it, hey, how about f hat? F hat of t. Could I draw these things as arrows if I like? Sure, if you want. Not that functions are literally arrows, but just for the sake of thinking about triangles here in this picture. F hat's an orthogonal projection of f onto the subspace, and therefore this distance is minimized. Distance is minimized. F hat, the orthogonal projection, is the closest function in this function space to f of t equals t. And by closest function, that has a graphical interpretation as well. Now we're running low on time. What do you have to do for your problem? Your problem, you have t instead of t squared. But what you have to do is you have to find the orthogonal projection of f onto this subspace. Effectively, you have to use this formula right here. Yikes. Which means doing a bunch of integrals. Yikes. Mathematica, do it for me. Guess what? A bunch of the integrals are 0. For your example, where f of t is t, when you do these integrals, when f of t is t, you're multiplying an odd function times an even function. That's an odd function. That's not the same thing that happens with numbers. When you multiply, said the wrong thing. You multiply an odd function times an even function, it's an odd function. Not the same as with numbers. Odd number times an even number is an even number. But with functions, that analogy breaks down. An odd function times an even function is an odd function. This integral is an integral over an interval centered on 0. That integral is going to be 0 because you're integrating an odd function over an interval centered on 0. For this one, you'll be integrating t times sine of kt, and odd times an odd is an even function. You can double the integral from 0 to pi, makes the integrals a little easier to do. But you will have to use a bit of integration by parts to do it, yet again. If I'm going to do it with t squared there, I'd have to use integration by parts. With t squared, these integrals go away to 0, and these integrals are the ones that are non-zero. Let me just have Mathematica do it. You can certainly check your answers with Mathematica. And here's kind of a fun way to do it. Mathematica, I'm going to create a function that I'm going to call inner product fg to integrate this from negative pi to pi, this product. Can I do this in Mathematica? Sure. Now I can define f of t to be my function t squared, and Okay, what should I pick for g of t? Well, different things. Like if I want to integrate it against cosine, for example, I can do inner product, once I've defined these functions, inner product fg, negative 4 pi. It did it. If I change it to cosine of 2t and then do the inner product, I get pi. I get a different answer. Cosine of 3t, inner product, I get yet a different answer, negative 4 pi over 9, etc. If I picked a sine for this example, the inner product is going to be 0. Even function times an odd function is an odd function. Integrating from negative pi to pi, I'm going to get 0. Sine 4t, I'll still get 0. You also, in this formula, do need to normalize these things. You do need to divide by some inner products. This is the orthogonal decomposition theorem being here used. So notice in all these fractions, there are also some inner products. Those numbers are not 0, otherwise you'd be dividing by 0. So you're going to be doing inner product of, for example, if I have the inner product of sine of 4t with itself, I could do g comma g. I will not get 0. I get pi, it turns out, in this case. What's going to be helpful in doing that by hand is a couple trig identities. Cos squared of an arbitrary input, call it theta, is 1/2 plus 1/2 cos 2 theta. And sine squared theta is 1/2 minus 1/2 cos 2 theta, actually. Even though that's a sine, that's still a cosine. Maybe you've used these identities in Calc 2 or in multi. These are handy identities to use to help you do more integrals, and you can avoid integration by parts there. Okay, it's worth doing a Fourier polynomial by hand once. Ultimately, in the end, you use this final formula right there. And notice the a sub 0 gets divided by 2. And the reason that gets divided by 2 is because the inner product of 1 with itself over the interval from negative pi to pi is 2 pi instead of pi. So that's why you need an extra factor of 2 there. That's the final formula you use to write down. And what should happen in the end is if you do this for a high enough value of n, a high enough degree Fourier polynomial, if you graph the original function and the Fourier polynomial over the interval from negative pi to pi, the graphs are very close together. F hat is a good approximation to F. That's the point. And in the infinite sum with Fourier series, you get equality, which is a really handy thing, it turns out, for partial differential equations and other things, other applications as well, signal processing applications. Fourier series come up a lot. For the fast Fourier transform, the big thing in signal processing, it's all related.